The next equation can be written as E for non-standard condition is equal to standard E cell minus RT over NF ln Q, where Q is the reaction quotient. And from our previous video, if you haven't watched that, kindly do. We came to the realization that at temperature is equal to 25 degrees Celsius, we can further simplify the constants to give us E equals E naught minus 0.0591 over N Q, meaning RT over F has been dealt with. So in this particular questions, we are going to find out which of these equations to use given a question or given a problem. First of all, let's find out how we determine Q. Q should be equal to concentration of the product raised to stoichiometry over concentration of your reactants, also raised to stoichiometry. So for every given reaction, taking the first question, we have zinc as the anode, so it undergoes oxidation of zinc to give us zinc 2 plus. And we also have copper undergoing reduction, giving us copper. So as you see from question 1, you can see that we have a cell notation for the cell. The left-hand side is the oxidation half and the right-hand side is the reduction half. So this clearly showed that the zinc is the oxidation half and the copper is the reduction half. So we can now say that Q should be the concentration of the reactant. Based on these equations, we see that the electrolyte of the oxidation half is at the product and the electrolyte of the reduction half is at the reactant side. So Q should be equal to concentration of the oxidation electrolyte raised to the power A over the concentration of the reduction electrolyte raised to the power B, where A is the stoichiometry of the electrolyte. In question 1, we have to consider the E naught under standard conditions first. So E naught is calculated as the potential at the right hand side minus the potential at the left hand side. So that should be that of copper, which is 0.34 minus 0.76, and that gives us 1.1 volts. E is equal to E naught, which is 1.1 minus N RT over NF ln Q. Q is going to be 1 because the concentration of zinc and copper are both 1 as shown in the question. Okay, because they are both 1, ln of 1 goes to 0 and means that because this side is being multiplied, everything here goes to 0, and E will be equal to E naught, which is equal to 1.1 volts. So that's the end of the first question. For question 2, we see that even though we have two expressions of the equation, we cannot use the first one because the E equal to E naught minus 0.0591 log Q over N is not going to hold because this particular reaction is at 50 degrees Celsius. We can't use this equation. So we'll use the other one, which is E equals E naught minus RT over NF ln Q. E naught will be equal to, again, the copper is at the oxidation half, it's at the left, okay? So we have to do the reduction half minus the oxidation half, or the right side minus the left side. So the right side is silver, which is 0.80, minus the left side, which is the copper, which is going to be 0.34 volts. So that gives us 0.80 minus 0.34, which is 0.46 volts. And the nRT over NF gives us 8.314 times, we had 50, so 50 plus 273, we'll convert it to Kelvin, which is 323 Kelvin. We have 2 electrons involved in the process, and then the Faraday's constant. So let's solve this. This times 8.314 divided by 2 divided by 96,500 gives us 0.013914. Okay, now we have to multiply this by ln Q. Okay, so let's find ln Q. Q will be equal to the concentration of copper, which is the oxidation side, 0.1, divided by the concentration of silver, which is 0.010 raised to the stoichiometry 1 and raised to the stoichiometry 2. How did we arrive at the 1 and 2? Copper is undergoing oxidation to form copper 2 plus, 2 electrons. Silver is undergoing reduction to form silver. And for the electrons to balance out, we multiply the second equation by 2 to cancel out the number of electrons. And given that, we can see that we need 2 silver ions. Okay, so that's why we have 2 here. This gives us 1000, and then the ln of 1000 gives us 6.909. So when we come back to E, it's E naught, which is 0.46 minus nRT over, which we already have here, 0.013 times ln Q, which is 6.909. So let's calculate for this. So the 0.0139 times 6.909 gives us 0.096 132. So we have 0.46 minus 0.096132. which is approximately 0.36 volts. We see a reduction in the voltage because you see here we had, for the standard condition, the voltage is 0.46, but under these conditions we had 0.36, and we can clearly see that it's because the reaction quotient, we have a higher concentration of the product, which was 0.1, and the reactant was rather 0.01 to the power 2. So that showed the reason why the reaction was, more work was not derived, but less work is derived from the cell. To make the cell produce more work, you have to reduce the concentration at the anodic side and increase the concentration at the cathodic side. So watch the previous videos for further explanation. So at the end of that, we had 0.36 as the final voltage for question 2. Let's do question 3 quickly. Here we are considering an electrolysis cell which is made up of zinc and copper electrodes. Their reduction potentials are given. Now, how do you know which is the anode and which is the cathode? In a galvanic cell, if you watch the previous video, you see that the more negative electrode, which is the zinc, and the copper is a more positive electrode, which is 0.34 plus. So this is a more positive one. The more negative one is the anode in a galvanic cell, and the more positive one is the cathode. However, in an electrolysis cell, the more positive electrode acts as the anode, and the more negative electron acts as the cathode, even though it prefers to lose. Yeah. So here we see that even though the zinc would have preferred to lose electrons and undergo oxidation, it will rather end up accepting the electrons. Okay. So if that is the case, then copper is going to be the right hand side. Copper is going to be the left hand side, the anode in an electrolysis cell. So the cell EMF should be equal to the right side, which is zinc, minus the anode, or the left side, which is copper. And this gives us minus 1.1 volts. Just the first question was positive 1.1. The third question is minus 1.1. And E cell again should be equal to E naught cell minus, because this is at 25 degrees Celsius, we can actually use the constant, the factor, the simplified factor, which is 0.0591 over n times the quotient. But Q here should be equal to 1 because both concentrations are 1 molar. So Q here will be equal to 1. Sorry, I'm so sorry. There should be a log here, log Q, right? So Q here should be equal to 1. Log 1 is equal to 0. So this whole portion is 0. Multiplied by this gives us another 0. And we see that the E cell should be equal to E cell naught, which is equal to 1 minus 1.1 volts. Again, this is a confirmation of electrolysis because you have a negative voltage, and converting that to Gibbs free energy gives you a positive Gibbs free energy. Okay, so that brings us to the end of this video. See you in the next one. Bye.